Okay, hi everyone. Let's have a look at question 8 from the D1 2009 January paper. And this is a critical path analysis question. And what we can see is, well, first of all, if you don't know what this means, you might want to have a look back at the video we did for question 3, which gets you to draw a activity network. But assuming you're okay with this, let's just go into part A. So you've got an activity network. We have to put on the early times and the late times for each event. So let's have a look at what we're given in the answer booklet. Whoops, this thing. Okay, this is what you're given, and we have to fill in these boxes. Now the top box is the early times and the bottom box is the late times. And basically with the early times we're asking the question, at what point can we move on from this event? What's the earliest that this, what point is everything that needs to be done so we can move on? Let me show you a couple of examples. So the earliest time we can move on from this node is obviously 0. We can start it straight away. Then we go up here. The earliest time we can move on from here is obviously 0 plus 10, because it takes 10, I think it's days to get here. Same with B, 0 plus 4, that's 4. We can move on after 4 days. Now if we have a look at this node here, we're gonna ask the question, when can we move on? So it will take 8 to get to here, 8 days, 4 plus 4 on that route, so we could put an 8 above here. But this route would take 10 plus 0, because you've got a dummy here, so it would take 10. And we can't move on until both paths are done, till everything's done. So actually we're going to have to take the highest number. And you can kind of think of it, imagine there's a little guy up here in a box waiting for you to give him the tickets from all the jobs that need to be done, and he won't let you go through until you've given him all the tickets. So we can't pass on until 10 days. Okay, so let's summarize this a bit. For the early time, we're considering what is coming in to the node. So we're asking the question, what is coming in? And we can't move on till all the tickets are in from every activity. So basically we have to take the highest number. So take the highest number. So let's carry on. So this one, only one thing coming in, so life is easy. 10 plus 5, 15. This one here, 2 things coming in, so 15 plus 3 is 18. Or 10 plus 10 is 20. So we're going to have to go with 20 because it's the highest. We can't move on till everything's done. Try this one here, 10 plus 9 is 19. 4 plus 14 is 18. Take the highest. Oh, excuse me, that is a 19, not an 18. Okay. Hope you can read that okay. It's supposed to say 19. Again here, 20 plus 2 is 22. 19 plus 7 is 26. Go with the highest, 26. Again here, 26 plus 8 is 34. 15 plus 15 is 30. Can't move on till everything's done, so it'll take 34. And finally, 34 plus 5 is 39. 19 plus 13 is 32. Take the highest, 39. Okay, now we filled in all our early times. let's look at the late times. Now this time we're asking the question, what's the latest time we can afford to leave without messing up the schedule? Let me show you an example. So once we've got the early time of 39, we fill that in on the second box. These two are always the same, these two will always be the same. And now we work backwards. So late time, ask what is leaving your node. Okay, so let's go here. Only one thing leaving, and the question is, how late can we afford to leave here and still be on time for 39 days? So clearly 39 minus 5 is 34. The latest we can leave here is at 34, because any later we wouldn't make it for 39. Again, we got this one, asking the question, what's leaving? That's going to be an important question, because there are two things leaving, so we do two calculations. Okay, so with this one, how late can we afford to leave this node here in order to still be on time for 39? Well, that's 39 minus 13, that's got to be 26. So we could leave as late as 26. But how late can we afford... Oh, we haven't got this one yet, so actually can't fill that one in yet. Excuse me, we'll come back to that in a sec. We have to fill this one in first. What's leaving this node? Only one thing, so 34 minus 8, well, that's 26. So we got to leave the latest 26 days. Got to leave here in order to be on time for 34. That's the latest time we can get here. Okay, so now we're ready to fill in this one. So 26 minus 7, that's 19. So the latest we could really leave here is not 26, because then we'd be too late for this one. It's 19. So you can see that what we're going to end up doing is taking the lowest number. Take the lowest number. Those are the two key principles. Let's go again. So what can we fill in now? Let's try this one. What's leaving? First question. Only one thing, so life is easy. 26 minus 2 is 24. So let's try this one. 34 minus 15, that's 19. And 24 minus 3, that's 21. I'm going to take the lowest number, because if we leave any later, we'll be late for this one here. Okay, same again down here. 24 minus 10, that is 14. 19 minus 9, that's 10. Take the lowest. Backtrack again. 10 minus 4, that's 6. 19 minus 14, there's a difference of 5. Take the lowest. Got to be 5. And then up here, 19 minus 5, that's 14. And then 10 minus 0, because the dummy has 0 weight, that's 10. This one's got to be 10 then. 10 minus 10, okay, trying this one. 10 minus 10 is 0. And 5 minus 4 is 1. Take the smallest, 0. These two numbers should always end up the same, and so should these two. So now we've filled in our early and late times. So we feel pretty good about that. Things going well. Let's take a look at the question. Part B says, determine the critical activities and the length of the critical path. Okay, let's try and get a bit of clarity on what this means. Okay, so the activities in this network are the arcs. These are the jobs that have to be done. And the nodes we call events. So these aren't actually specifically jobs, but they're kind of places in our schedule where we have to get to. And they're significant because, let's take this node, this event here, represents the fact that G and H have both been done, and now we're able to start activity J. Until these are both done, we can't start J, so this node, this event, is significant. So with the critical path analysis, it's important to be clear on the difference between a critical event and a critical activity. Now the critical events are quite easy to spot. Critical event, an event that's a node, is critical when the early and late times are both the same. That means there's no flexibility as to when you can get to this event. So the first one is critical. This one, 10 and 10. Yep, not that one, they're different. 10 and 10, 4 and 5, no. 19 and 19. 26, 26. 34, 34. 39, 39. These ones obviously will always be critical. The interesting part then is to work out the critical path, and the critical path goes between critical events. Sometimes it's obvious where that path is, other times not so obvious. And the way we can tell if an event is on the critical path is with this idea of a thing called a float. So let me just explain that. I'll give you an illustration. Let's just have a look at this node here and this node here and think about the activity G. So when's the earliest that we could possibly start G? We'll look at this time here. After 15 days we could start activity G. So imagine we start it there. And then how long does it take? Well, it takes 3 days. So let's just sort of illustrate that by saying G is going to take 3 days. So we can start at 15, it takes 3 days. The latest we're allowed, the latest that this event here can happen is 24 days. So 24 is over here. So think about how much slack is there, how much what are our options for when we can do G? Well, we could start it as early as 15, or we could finish it as late as 24. So how much float, how much space is there for us to move G around? Imagine this is on a slider. Well, 24, between 15 and 24 there's 9, and G takes 3, so there must be sort of 6 days left that we've got to play with. We can slide G, back and forth around, and this number we call the float. And the float really basically asking how much flexibility is there for you to do this task. And the way we define it is it's the latest time at the end, latest end time, take away the size of the activity. We take away, let's say, arc weight. That's the number on the arc, so 3, and then take away the earliest start time. And basically what you're left with is the slack. So this will hopefully be useful to you later. So we can see that the float on G is 24 minus 3, that's 21, minus 19, that leaves us with 3, so we've got 3 days to play with. Now, why am I telling you this? Is because the critical activities, the arcs, are those activities which have a float of 0. That means you've got no time to play with. You have to start them when you've got to start them, and you have to finish them, and there's no room to slide them around. So let's just illustrate that. Let's ask the question, is this activity L critical? So you got 39, that's the latest end time. So look to the end. 39 minus the arc weight, that's 13. So that takes us down to 26. And then take away the earliest start time. So 26 minus 19, that's 7. So there's a float 7 on the activity L. So it's not critical because you can play around with it. You can move it back and forth by 7 days. How about N though? 39 minus 5 is 34 minus 34. There's a float of 0 on N, so there's no way you can move it back or forth. So it is a critical activity, so it's going to be on the critical path. And this is useful to know because you can't always be completely sure if an activity is on the critical path just because it's between two critical events, because there may be two activities going between two critical events or something like that, and one of them might be critical and the other not. So it's worth being aware of that. But have a look at this setup we've got here, and between these two critical events there's only one arc, so there's only one possibility. So this must be on the critical path, and we can just check that. 10 minus 10 minus 0, there's no float. Okay, where's the next one? Well, it can't be this one because that's not a critical activity. So the only option is that it must be this dummy here. The next critical activity, well, it can't be this one. It must be that one because it has to join up two critical events and so on. It's actually quite obvious on this particular map, on this particular network, which are the critical activities. Take your critical activities, write them in a row, and you've got your critical path. So let's just put that on. Critical path. So A, that's a dummy, so that doesn't actually have a label, so we don't actually need to include that in our path. I, next K, M and N. That is our critical path. So looking back at the question, determine the critical activities, we've done that, and the length of the critical path, well, that's simply done by adding up the weights of the activities, so 10 plus 0 plus 9 plus 19 plus 7 is 26 plus 8 is 34 plus 5, that's 39. And actually you don't need to do that because you can see the length of the shortest time that the project can be done in is 39, and that will always be the length of the critical path, because the critical path is by definition the path for which there's no flexibility. So this one has to be done in the shortest possible time, which is 39. So the length of the critical path would always be this number here. Okay, brilliant. So let's move on and have a look at part C. Calculate the total float on activities F and G. You must make the numbers you used in your calculation clear. So let's have a look at what we've got. Made a bit of space down here. Well, we just talked about how to do float, didn't we? So let's do that for F and G. So float on F, latest end time 34 minus arc weight, that's 15, so that gets us to 19, minus earliest start time. So let's write this down. Float on F. So we said latest end time 34 minus the weight 15 minus the earliest start time, that is also 15. So 34 minus 30, that leaves us with 4. So the float is 4. And just one more time, I'll just show you what that means in common sense terms. The earliest we can start F is at 15, and it takes 15 days to do. So this is F, that's taking 15 days, and that gets us up to 30 days. But the latest we can get to this event here is 34. So there's a bit of slack as to when we can do F. We can start it a bit later. We can start it up to 4 days later, or we can start it any time in between. But the float, if that was a little, I don't know, a boat, it could float by 4 days either direction. So that's what's going on there. So float on G, I think we already did this. It was 24 minus 3 minus 15. So that's 24 minus 18. So that leaves us with 6. So we've got 6 days to play with when thinking about when to do G. Okay, so we're looking good so far. The final part of the question, final 2 parts, is to do a Gantt chart. And I'm going to do that in a separate video, so check that one out as well.